of the base station, because you would need some of them to serve one user and some of them to serve another user, right? And the multiplexing gain in this case is given by the sum of the streams you transmit to the different users, right? The limitation here is more on the base station side, okay? So these things have been there for a while. These are already in the standards. Some products have them. For example, Wi-Fi uses some sort of MIMO, right? And multi-user MIMO is in LTE. So this has happened. So now, given that MIMO has been there for a while, what's next? Okay, so there are three flavors of MIMO that appear to be relevant for the 5G systems. One is what we call coordinated MIMO. We already saw it a couple of times in this course. In the past, it used to be called network MIMO or virtual MIMO, cooperative MIMO. So it has different names depending on the people working on the system. But in the main idea is that you coordinate physically separated antennas to produce a certain joint effort in transmission. So there are, this is also called in the LTE terminology COMP, coordinated multipoint. They're all the same thing. So what you do, I mean, at least I'm talking about LTE, the flavors are three. So there is, in order of increasing complexity and capabilities, you have coordinated scheduling, coordinated beamforming, and then joint transmission. This is, roughly speaking, the three categories. So coordinated scheduling simply means this is not even a proper MIMO in a sense. You could have coordinated scheduling with single antenna system. It simply means that different base stations would agree on which users to schedule on what resources, right? You coordinate the scheduling between different cells. Coordinated beamforming is sort of like that, plus you have beamforming capabilities of at your base station, so you become more granular in the set of actions you can take, right? You could say, okay, if I'm transmitting in this direction as a base station, you should not, right? So the only case where you would interfere is when the beams are basically co-aligned. So you do introduce more flexibility. The last bit, which is the most ambitious one, it's also the most far-fetched, is what we call joint processing. Joint processing basically means that you do share channel state information and data between the different base stations, and you act as if you were really a co-located array. What I mean is that you try to transmit a coordinated signal from the three base stations. Could be beamforming, could be other things like multiplexing, and you do it as if the antennas were in the same place. So to do that, you need to exchange signals and have a picture of the channel state information. That's what you need for pre-coding, for example. And you also need to share the data, right? Depending on the capabilities and the requirements, we are moving from something that is basically already happening to something that will maybe not happen before some time. The second flavor is the proper massive MIMO. So in a sense, these are all massive MIMO if you want, but the massive MIMO, as normal is we refer to in the literature, it means co-located array of antennas. So you have maybe this kind of cylindric antennas or square antennas where you have a lot of radiating elements, and there are experiments with more than 100 already. Okay, it works. Now the advantages of massive MIMO are manifold. So first of all, if you can do beamforming with MIMO, of course you can do it with massive MIMO, and it becomes much more precise. You create what we call pencil beams, so you become really very narrow in the beam you transmit, which leads to higher energy efficiency on the base station side. You waste less power. It becomes also better for the mobile phone because it boosts the signal to noise ratio, and it becomes beneficial in terms of interference, right? Because I'm just interfering potentially with somebody that might transmit along the same line, right? But if the other person transmits along another line, then we won't see each other. So this leads basically to a situation like this where you see all different colors mean different streams, which you send simultaneously to many users. So because you separate so nicely the users in space, you don't need to bother too much about scheduling. So one consequence of massive MIMO is that it simplifies to some extent the radio resource management. Possibly you could say that there is a complete reuse of the spectrum. Okay, now the picture is a bit gloomier than this, because you do have a problem which we call pilot contamination, which I'm going back to later. The third flavor, which appears to be there in the 5G community, is the millimeter wave MIMO. So this basically implies that we are using high bands, right? Definitely beyond 28 gigahertz, and then some people say 60, some people say 70, some people say 90. So there are different opinions and different systems. The WiGig system 802.16ad is using 60 gigahertz. That's the standard of Wi-Fi, right? So things have been happening. Now, why does it need to be MIMO? No, it doesn't. It can be a simple single antenna system, but it makes a lot of sense to consider MIMO in a millimeter wave band because, as I mentioned already in this course, the rule of thumb to separate antennas so that they don't, say, correlate too much and you can reap most of the benefits of MIMO, so the requirement is that the antennas have to be spaced by, roughly speaking, half the wavelength. Now the wavelength is inversely proportional to the frequency, right? So the higher the frequency, the lower the wavelength. Therefore, ideally, given the same physical distance, say mobile phone, back plane, you can actually squeeze more antennas. So it makes sense. Now it's not so cheap. There are hardware complications, okay, and there are some things that still have to be sorted out, but people are working on that, okay? So when you talk about millimeter wave MIMO, you implicitly mean beamforming. You do need to use beamforming because the millimeter wave bands are very sensitive to line of sight blockage, right? So you really need to identify where the user is and transmit in line of sight to the user. Otherwise, you start to be in trouble. So it doesn't really make a lot of difference whether you have multipath reflections or not, because likely any reflection will come too much attenuated at the receiver, will arrive too attenuated at the receiver. Okay, so you do need to have beamforming in this sense. So in the main, this the sort of fact sheet about massive MIMO. Okay, that's what's happening. Yes. Yes.
It is one of the aspects apart from the diversity.
Yes.
But beamforming is one of
I
the.
think it is one of the definitely the main aspects, but I don't think it's the only one. Okay, so there are other. Definitely it is, especially for millimeter wave. Then we're talking beamforming, definitely.
When we talk of beamforming, you have to do some sort of phase shifting within the array. So how do you do it? Because it has to be switched for different users. Because one user may be in this direction.
Yes. Yeah. One big problem actually is still, I think, people are working on is tracking, right? So you do need to track users. So what changes, for example, compared to other short-range communications like small cells, here is that the transmission is not omnidirectional anymore. It is actually very directional. So you have to keep tracking the users. And I think one problem with the traditional way to do beamforming is that it takes a lot of time before you readjust. It is slow. Okay, so the time scale by which you could say physically shift your antennas, okay, and track the users, it's not a good match. Okay, so it is too slow for possibly the mobility of users. There are discussions, especially millimeter wave, whether it's better to do it in a digital or analog form or combinations. Now, to answer properly this question, I should be an RF engineer. I'm not. Okay, I have some basics, but I'm not doing research on that. So what I can tell you is that when I talk to people that are working in RF, they are not too happy to hear about these things. Okay, so that the combination of having many antennas and having millimeter wave is very complicated. It's already difficult, one of the two. If you have both, starts to be complicated.
If the number of users increases, it is more number of beams you have to.
Yes.
It means more number of times you have to switch.
Correct. Yeah. No. This is a problem. Yes, definitely, it is a problem. I think people are working on that now. In fairness, what I could see in my work on massive MIMO is that sometimes you don't need so many antennas. In the sense that it has a lot to play with the amount of spatial richness you can harvest, right? So how rich is your environment in terms of scatters has a direct impact on the performance of MIMO. This is well known from the MIMO work. So because in millimeter wave you're very kind of constrained in terms of the range, it could be that anyway you won't benefit too much out of massive MIMO because there is simply not enough scattering, right? I don't know. This is an hypothesis. We are still, seeing what happens. But my experience from, say, other bands is that sometimes massive MIMO ceases to be useful if, let's say, you're in a poorly scattered environment already after 10 to 20 antennas. So what I'm saying here is that, yes, it's complicated, but it could be anyway that you don't have to go beyond 5 to 10 antennas, maybe, okay? So that would simplify some things. Another thing is, you have to track users. Do they really move always that fast? Maybe not, right? It's scenario dependent. So if you are in a hotspot, kind of an airport, I mean, how fast can you move? Come on. I mean, you are going to, go to the coffee vendor machine, right? Vending machine, or, go and pick a paper. I mean, you go to the corner to make a call, but you're not running, right, crazily in the airport. So I think some things will come, your way in a sense, but in general, it's challenging, this problem of user tracking and adjustment of the beamformer to that. It is this problem people are working on. I think in general there is not still a consensus whether it should be digital or analog or combination. And so one thing I think is needed if you want to work on this, and we have a project in collaboration with Virginia Tech and University of Belfast, is to have people that are hardware people in the team, okay? Because otherwise you tend to do communication theoretical works or simulative works, but you miss a bit the point. So I think you really have to take into account RF input, okay? So these things are very important, especially when you have millimeter wave involved. Okay. Question? Yes. Yes. Yeah. I mean, of course, the more. What is the number? Yeah. Well, I think people are normally talking about hundreds. So that the prototypes I'm aware of, they have about 120 something. Okay, maybe a bit more. Now, one thing I'm a bit puzzled is that before people were talking up to 16, now they talk immediately 100. I suppose what will happen in truth is that next step will be maybe 20 or 30. I don't think it will go all the way immediately to 100. So you can still benefit a lot, without having 100. So you can create narrower beams with maybe just twice the antennas we have nowadays at the base station. But normally, I mean, the number people talk about, it's like 10 times higher than the number of users. Now, the number of users nowadays are normally that LTE can accommodate at any scheduling session. We are talking maybe 15, 20, okay, co-schedule at the same time. So 10 times that gives you an idea. Now, an important thing to consider is the array processing gain you can get from massive MIMO, which is 10 log 10 of the number of antennas at the base station. So that gives you an idea of the boost you can get out of a massive MIMO beamforming. So, for example, if you have 100 antennas, you can boost it by 20 dB, 10 log 10 of 100, right? It's 10 log 10 of 10 to the second, so that means 20 dB, and so on, right? So you will have to design, you know, how narrow your beam is, and eventually how much you boost the SNR. You know, you will have, in a sense, to reverse engineer, I suppose. So if that receiver needs that boost, then you will need so many antennas, and it's not too complicated to do. Okay, it's link budget thing. Okay, so now to dig a bit deeper into the possible MIMO families. So let's start with network MIMO, or cooperative MIMO, or coordinated multipoint, or virtual MIMO. You call it as you want. Okay, it doesn't matter. So in the main, you have a coordinated transmission between base stations, right? Yeah, as I said, it has different names. One of the main concepts is to try to turn the interference from foe to friend. So what it means is that since you are coordinating with other base stations, you know, trivially, since they are working together with you, their transmission won't be interference anymore, will be part of the joint transmission signal, right? Of course, there are some requirements in terms of the black hole, because you need to exchange quickly information between base stations, which might be actually quite a bit far apart. So this doesn't need to be small cells, right? It could be macro cells. So we're talking kilometers, possibly, of distance. And if you have the more ambitious version, the most ambitious version, which is joint transmission, you don't only need to transmit a few bits telling you the channel quantized quality, but you might also need to share the data, which might be a lot of capacity, right? You need to have available. So a good backhaul is key. If you don't have a good backhaul, this is not a good choice. Yeah, you do improve area spectral efficiency. So it's not just the spectral efficiency, it's also the area spectral efficiency, because you are covering now certain area, right? And yeah, of course, you want to improve the system capacity. And I mean, to my understanding, this scheme didn't give impressive gains in terms of average cell throughput, but it gave decent gains in the trial so far, at least on the cell edge throughput side. So it's more meant, in a sense, to improve coverage, which kind of makes sense, because you are coordinating the transmissions, and where you have most of the inter-cell problems is at the cell boundary. That's where you have the outage problem. So if you do coordinate transmissions between base stations, you would expect that outage gets better, which is the case, in fact. It used to be called, I mean, the early ideas on similar technologies when I was doing my PhD were called macro diversity, right? You would have these independent separate base station, which would kind of collaborate to form, to basically create an Alamuti signal, right? So that has been there for a while, okay? And then there's been, you know, refinements to the idea and improvements, but I heard the first time about this definitely more than 10 years ago. So a lot of work is up. Any question or comment?
How do you understand what sort of coordination will be there? I mean, how they will coordinate and how MIMO comes into the play?
Yeah, right. So I think there are, you know, the real network MIMO is what we call joint transmission. So practically what you will have, you have to think like what you would do with MIMO. Okay, so what you would transmit for each antenna. And now you would have the same, but just that the antennas are not in the same place. Okay, so for example, when you do pre-coding, what you need to do is basically to multiply a certain matrix, right? Pre-coding matrix to the transmit signal. So now if you want to do it in a distributed way, you have basically to consider which part of the pre-coding matrix you should transmit from which antenna. So you have to decide. Okay, so there is an association between what you transmit and the antenna. It's the same thing, just that now, you know, you will have maybe, say you have, let me think. Okay, so, okay, say you have the channel is, the size of the channel matrix would be number of receive antennas times number of transmit. Yes. The user transmit vector would be number of transmit antennas times 1. So the precoding matrix would be NT times NT, right? Transmit antennas numbers times transmit antenna numbers. So there will be a one-to-one mapping between the, for example, the row, right, of the precoding matrix and the antenna. So you will have to decide, right, which row goes into which antenna. And you will also have, but these all multiply the same data, right? So there is a part to do with say the precoding, but there is also a part to do with data. So you need to share the data, correct? To all, it's the same data vector, right? So regardless of the row that multiplies the data vector, this has to be shared, right? I don't want to go into many details because it gets complicated, but there are papers that explain the basics and so on. But the idea is that you do what you do with MIMO, just you have to decide what goes into what antenna, right? And some things have to be shared, like the data have to be shared. Okay, so you do need to act quickly and with high capacity. There was a question from the front row, I think. Yeah. Coded MIMO? Coordinated MIMO, yes, same thing. It will, they use many different names. So coordinated MIMO, cooperative MIMO, network MIMO, virtual MIMO, there's plenty of names. Okay, comp. There are, I think there are some things that are a bit lighter in requirements of the data exchange. For example, if you do coordinated scheduling, that doesn't imply that you do joint MIMO transmission, but you still need to know which resources are used by the other cells. So they have to send you a matrix in a sense. What this matrix will be a time frequency grid. They will tell you what they are using. So you need to quantize this, right, and send it to the other base station. So what I'm doing has to be say I'm this antenna and I do something with my users. I have to tell to the other two this, and vice versa, right? So there is this exchange of sort of control information, right? So depending on what you want to do with the coordination, you will need more or less exchange of information here.
You are telling that this scheme will be fruitful when only when you have good backhaul connection.
Yes.
Backhaul means where base station is behind equally.
Pretty much. Well, that's the version of this which is Cloud Run, okay, which is kind of, or let's say the version where they have the antennas to be dumped. This is not necessarily that. Okay, this could be the antenna. The base stations are basically pretty okay, normal, right? So they're not dumb by F. These are real base stations. So then the intelligence would be in these transmitters. Okay, but what you would have if you have a Cloud Run, then yes, you would have the intelligence maybe somewhere. So that's, I'm going back to it, but this, depending on how much you want, where you want to put your intelligence in the network, you will have different flavors to this. Okay. But even if you do the dumb version, one possibility is to do the digital radio over fiber. You need a lot of bandwidth for that too. So regardless of whether you have the intelligence here or the intelligence here, these schemes are backhaul heavy. Okay, they do require a good backhaul, regardless of the flavor of the technique.
Traditional cloud run backhaul exists between baseband pool and in between baseband pool.
Yes.
And
yes.
So that is
No. Yeah. Okay. Maybe this is backhaul because, I see your point. This is backhaul because it connects the base stations, okay, to the rest of the network. So that's called backhaul, at least to my knowledge. When you have Cloud Run, this link would be called front haul. It's haul, okay, but not backhaul. Yes, that's true. So you would have front haul from the remote radio head to the baseband unit, and then from there on you would have the backhaul, right? Yes, that's correct. I think here we are implicitly talking about a version where you have not Cloud Run, so you have intelligent base stations here. Even if you have Cloud Run, though, you need a very good front haul. So you do need good cabling from the radiating element to the rest of the network. That's true regardless, I think, of the technology. Okay.
But in cloud, and how do you come across this interference, other question interference? Like baseband for each baseband
Yes.
will be doing signal processing for one cluster only. Whatever RRHs included in that cluster,
Yes.
every pool
Yes.
giant processing.
Correct. I mean, in fact, this is like, this implicitly means comp. So comp is not the same thing as Cloud Run. I'm going back to this later on. But here we are not necessarily talking Cloud Run. Okay, this is like different base stations. They try to cooperate so they don't interfere with each other. In Cloud Run, you're right. So what probably you would have, well, of course, you would have no interference within your cluster, right, of remote radio heads if you do things properly with pre-coding. But then there is the open problem of the other clusters. Anyway, there will be the same problem here if you change cluster of base stations, right? Because say that your pattern is 3 base stations cooperating, you are not cooperating with everybody else, right? So you still have a problem of if not inter-cell or inter-base station interference, inter-cluster interference, right? I didn't work on that. I assume there is work. So this would become kind of a layered resource allocation problem, right? And you would need some decisions to be taken. So probably a scalable one is not the centralized one, because eventually, it becomes too messy. Maybe every cluster should just act in a self-organizing way, right? They should just take some decisions based on the interference picture. So it's like you act at the cluster level instead of at the cell level, but still you act independent. It's what they do with small cell networks, SATNet, right? There is work on that. So it's the old, dilemma: do I do it centralized or distributed? Again, it's part of that. I didn't work on that, but this is definitely an interesting problem. Okay, so that goes back to your point. So there are a few things you can do. Okay, so this case we saw before is more this, right? You coordinate over backhaul, and then you have, for example, the Cloud Run, where you have possibly the processing for many base stations in the cloud, and then you have maybe many BBUs here, baseband units. In the main, though, what you want to achieve is similar. You want the different antennas, instead of interfering each other, to act together and to create some joint transmission capabilities. Okay. Now, this distributed antenna systems, or DAS, might even be known to some of you because they have been there for a while. For example, in a corporate building, possibly that's the way they would provide coverage to different stories, right? You would have an antenna, an access point for each story, and then there would be a central unit kind of, distributing for example, the bandwidth or managing the power, right? And it's kind of there for a while. So this has been implemented for a while. So if you want, many of these concepts, which are a bit more advanced, like comp and Cloud Run, they sort of root themselves in DAS. Okay, this is the first time where you have this kind of distributed multiple antenna capability. Now, going back to the point of your colleague here, yes, I mean, how you basically manage the intercluster interference is key. Probably is one of the main problems. And you could have different things. You could have more static things. You could have more dynamic things where the clusters change, right? Though here we move into a more possibly frequency planning domain, right? And yeah, frequency planning must be there, but you would also have to decide with which clusters to which cluster you belong, right? And now you form the clusters and so on. I suppose it definitely would depend, I guess, on the mobility of users, my guess, right? Yeah, so if the users tend not to move too much, possibly the situation won't change so much. So you might be happy with more static situations. But if you have like more mobility, then possibly you need to rearrange the clusters, right? Because eventually, I don't expect a huge amount of variation in the infrastructure, right? I mean, once you have your base stations, that's what you have. But you might have quite some variation in the movement of the users and the traffic demand. So I think that's probably what would guide the formation of these clusters. Yeah? But it is a relevant problem, definitely. Okay, just some key points before we move on. So let's see if there is something I didn't say before. Yeah, I mean, just to point out, this is already there in 4G. There's something at least. It's going to be part of 5G too, possibly with extension to small cells and more antennas, cloud run, really picking up millimeter waves. So there's going to be integration from different angles, but this is already there in LTE standard, LTE advanced. It's been there as early as, if I'm not wrong, 2012. Okay, so this is definitely already considered. Yeah, I mean, it could be that the real cloud run access network, radio access network, could be the end point of this evolution, but still open for discussion. Now, going back to massive MIMO, so massive MIMO here in this context, I mean, these are all sort of massive MIMO systems. Potentially, any of these systems I'm talking about could be extended to many antennas, but when I say massive MIMO more specifically here, I mean many antennas, but at the base station, okay, in the same place. So you would have this M much greater than K. How much greater? 10. The rule of thumb is that it should be 10 times. You should have 10 times more antennas than number of users. If you look at it, practically what you do, you will distinguish your users based on the vector containing the different channel gains. Okay, so the user one would be associated with a vector containing the components H11 up to H1M and so on. Now that might ring a bell or two, and this is exactly what we did with CDMA. So looking at things from a kind of with higher level perspective, you would have a similar approach than you have with CDMA. In fact, they all share the same frequency, and you do have some sort of codes. Now, strictly speaking, the difference with CDMA is that these codes are not necessarily orthogonal, okay? But the things tend to be pretty orthogonal with increasing the number of antennas, okay? So if you do take the cross product of these vectors, when you have the scalar product of these vectors, when you have many antennas, it will increasingly likely be zero. And that's why the multi-user interference and the noise in these massive MIMO systems is increasingly small and tend to vanish when the number of antennas is infinity. Okay. By the way, if you look at it, just a question out of the blue, can you call OFDM a code-based system itself? You know, we think of CDMA as something else, but in the main, anybody? Sashank. And we say OFDM is kind of CDMA to some extent, in terms of, you know, having orthogonal codes allocated to users and so on. Yeah, right? That's how you orthogonalize subcarriers, right? So don't, you know, just a tip, when you talk, you know, about technical subjects, don't be compartmental. This is this, and this is this. You know, good ideas, they tend to propagate. So sometimes we call them differently, but in the main, same story. Massive MIMO is another example. You have to separate the users' communications eventually. Okay, that's all there is. Okay, there are two, of course, two scenarios of relevance, as always in communication, uplink and downlink. So in uplink, the problem is that, well, as we said, potentially you can allocate all the users in the same band in the same region, right? Because you will separate them at the base station with the degrees of freedom provided by the antennas. What though we didn't say so far, at least not too much, it's how about channel estimation? Because you do need to get an idea of the channels, right? Of the links between the users and the base station. So what you do normally, you basically tell to the different users, you allocate some pilot sequences, right? And basically then they will transmit this, right? And because you know the pilot will be able to estimate the channel, okay? as always we do with pilots. Now, what's the problem here? The problem is, ideally, you should never have this situation where two users belonging to two different cells use the same pilot. Why? Because eventually they're going to interfere, right? They use the same frequency and they use on top of it the same pilot, so no way you can distinguish the two. So they're going to interfere not in the communication anymore, but on the estimation phase now. Yes?
Can't we obviate this problem by simply defining a threshold power level?
Yes, okay, there are solutions. I'm stating the problem here. I'm not saying it's unsolvable, right? My group itself has a couple of publications how to solve pilot contamination. So, I think there might be a solution along those lines. If not, write a paper and publish. But there are solutions. There are quite a few. Actually, this is a very active area of research. This pilot decontamination. So, it's been there. So I'm just stating a problem, but there are solutions. So the main issue here is why you have this problem is that ideally you should consider any cluster of cells and avoid the situation where you have the same pilot assigned to users in different cells, right? I mean, if I have 6 and I have 3 users per cell, okay, I use ABC and the others use DEF. Easy peasy, right? What's the problem then? Why don't we do that? Anybody guessing why we actually have this issue? Because I mean, if you could just allocate, different pilots, you don't have any problem, right? So why can't you do that? Why do you have somehow to?
It's a very costly channel, the control channel pilot system.
Correct.
Do it generally for more than 70 channels. Like in
Yes, there is that.
Of 63 channels, and
that's correct. You have a limited set, right? So
having a system with we have system with 6 to 7 pilots, but then that depends how much is the configuration. Even having 2 pilots in a system is again very costly.
Correct. Definitely that's an issue. But say you have enough, okay, and say you have between say 3-4 cells that are nearby, you have a number of users which is less than that amount. Then you could, right? You could say, okay, I use this subset. So what's the problem? Why can't we do that even in this case? Or normally we can't.
Generally, in downlink process, usage at the origin, base stations are generally distributed, right? In the second case, how it is?
Is downlink, yeah? So what's your question, sorry, again?
Usage at the origin, base stations are distributed, right?
Yes.
But here, base station is at the origin.
Yes.
Users are distributed. How it is?
No, this is not the distributed case. These are all collocated, right? So this is like a massive array. This is another massive array. So this is different than before. They might not even coordinate. Okay. It could be. You could have a combination of this massive MIMO and the cooperative. It could. Okay, but in this case, I'm not necessarily assuming it. So anybody guessing what's the problem here? Why can't we?
The number of users in a cell would not be fixed.
Yeah, but you could, let's say, in a certain time interval, right, how many users you're going to serve. So the problem here, you see, is that you have some limitations with coherence time, right? The channel after a while, the channel information after a while gets outdated. So especially if you start to increase the cluster, even if, say, there is that problem, your colleague is right, that it's not easy to have many pilots, right, in the system. But even if you have, at some point you have to stop, right? And you have to, call it a day, okay, whatever, because it will take simply too long before you coordinate, right? And by then, it's not any use, right? You want to be quick. So what happens is that per cell normally, or per cluster probably, but definitely not in a not too broad area, you accept, okay, that some users in the other cell might be using your very same pilots, but you will cope with that somehow, okay? But that's what gives origin to this, gives rise to this problem, okay? Because if you could allocate the pilots, regardless of the complexity of the pilot scheme, regardless of the coherence time, you would do it, right? It would simply be an optimization problem. But there are constraints in complexity and time. Now, the reverse in the downlink, you get rid of interference, possibly, right? Why? Because basically, well, unless you're very unlucky, and you are really aligned with the transmissions, because of this kind of pencil beam transmission, you will decrease the intercell interference, right? Another problem, another assumption here, which makes things easier, is that you assume the channel not to change too drastically over time. Therefore, you can do TDD. So you can use the downlink transmission to get an idea of the uplink quality of the channel, right? So you exploit channel reciprocity. What's the catch here? Okay, when would you have a problem with this approach? Can you make an example of a scenario where this wouldn't probably work? So we are exploiting channel reciprocity here. So this is okay as long as anybody brave enough. I know you're recorded, so don't worry. Anyway, sure, people at home won't have much better clue. Yeah. Anybody? Yes, and what impacts that? Coherence time, yes, but what is changing that? Right, and when is it more challenging? When does it get worse? It's not one thing, right? So how does it change the coherence time? Yes, yes. So eye mobility would be kind of an enemy of this approach, right? Because we know that coherence time is inversely proportional, roughly speaking, to the velocity, right? So in very mobile scenarios, you might have problems here. That's what we call channel aging. Yeah. Or possibly very large areas. I don't know, right? These are scenarios where, I mean, physics dictates the limits here, right? But in the main, the approach, when you talk massive MIMO, you talk TDD. Some people have been starting to look into FDD. I don't think the progress is that fast because it's apparently very difficult, okay? A good thing is that maybe massive MIMO is meant to be used in combination with millimeter waves, so small cells, which apparently are going TDD, while the macro cell networks are possibly using FDD. So key facts, we already said some of these, I think actually all of them, if I'm not wrong, right? So this is just a summary, but we already touched all of these points. To give a visual representation of this, boost in the SNR, this is a result from a paper in 2013. They show what happens in terms of basically signal level, field strength, when you have a situation where you have 10 antennas in your array and when you have 100, and the color map tells you that the field strength is stronger for warmer colors and weaker for colder colors. So you see immediately that when you have a massive MIMO system, so 100 of antennas, you see this is a representation of this pencil thing, right? This is at the receiver. So you will have only one specific region where you're actually focusing your energy. And the rest is kind of very, very weak, right? That's exactly a good representation of what I've been saying so far. So this is from a paper, okay? So this is based on an experiment. I'm not sure this is experimentation or simulations, but it is actually a result, okay, in a research paper. Yeah, you could have solutions to pilot contamination. Some, for example, in my group, are based more on signal processing. Some are more based on resource allocation approach with game theory, other things. Okay, depends on how you look at things. There are solutions anyway. There is a lot of literature. Other things we already discussed. Yeah. Possibly massive MIMO won't be used in isolation, as we mentioned before. You could have, never think that things are siloed, right? It's not silos. Normally you have, it's not a silo. Normally you have, things can interact. For example, if you have cooperative MIMO and you have massive MIMO, you could have massive MIMO at different base stations, and they still could create a coordinated multi-point setup, right? Why not? And you could have even these plus millimeter wave, right? Why not? You would have like dense deployments where each base station is using millimeter wave band, massive MIMO, and then you coordinate things with, with a network MIMO approach. So you can have all of the possible combinations, right? And then, of course, the benefits would kind of hopefully sum up. Maybe not always, but you could see things that way. Just to close on millimeter wave, and we have already been saying a few things about this anyway. So these are the bands that are considering 1G up to 4G. They're all there. Okay, all the systems up to 4th generation, they use bands that are in the sweet spot, so to speak. Now, strictly speaking, if you go to the textbook definition of microwave, I think it would be all of this, right? But more practically speaking, we normally mean microwave below a few gigahertz. Doesn't have to be 3, it can be 6, okay? But millimeter wave, normally we start to talk about it from 28 gigahertz on, though, yeah, some people would call it also microwave, so there is some terminology issue. Sometimes you would hear 30 to 300 being called millimeter wave, and the bandwidth that is on the left side of the EM spectrum axis would be called centimeter wave. Be my guest. Okay, it doesn't matter. The thing is, when we talk millimeter wave, it's normally beyond 30 gigahertz, roughly speaking. Why do people turn to that? Well, they turn to that because there is spectrum, yes, but not an awful lot. For all the systems operating, in the lower portion of the spectrum, this is more or less what we have, okay? And all the systems are already using that. And you therefore need to push a lot on the spectrum efficiency side, right? Because the spectrum is only so much. So that's what, for example, led to all of these technologies, in a sense, increasing spectrum efficiency one way or another, or area spectral efficiency, maybe in the case of EThernet. But in millimeter wave, in a sense, you can afford to be a bit more sloppy in terms of spectral efficiency, simply because you have so much spectrum. Now, you can ask, wait a minute, okay, I'm sloppy, but therefore I interfere more. The thing is that in millimeter wave, you are more contained, right? So in a sense, you have to care a bit less, right? Because the propagation would help you. So you just have a lot of spectrum. Of course, there are problems, but these are the good things. Already used in LAN, PAN, VANET, vehicular ad hoc networks. In LAN, for example, there is WiGig, right? 802.16ad. So there are even products, I think, being available now. And another typical application of millimeter wave is backhauling, right? That has been suggested also. E-band, if I'm not wrong, we are talking beyond 70 gigahertz. Okay, so now we said a lot of this. I just want to emphasize a few more things. So larger bandwidth means higher noise power, right? The noise doesn't go away, the noise is there, and we know that in our Shannon equation, the noise plays a role, and it appears basically in the denominator of the SNR inside the logarithm, right? And we know also that it's not that increasing bandwidth forever will always play positive factor, right? We know that there is actually saturation, right? There's a number. So we are going towards this asymptote with millimeter wave, right? Because we use a lot of band. Right? So yes, it multiplies the logarithm linearly, but it also increases the noise. So at some point, is it worth it? Because you do complicate the technology a lot, right? You do need to get this band somehow, and you will have to put in place. We were talking before about tracking of users. So it's not for free, right? It's a new technology. It has to work. You have to solve problems, and you might end up in a situation where if you just exceed with the amount of bandwidth you use, you end up in a diminishing return situation. You spend a lot of money, right? Invest a lot of time, and maybe you just gain a tiny bit, right? Maybe there are better things. So what I'm trying to say here, keep an open mind. It's not that a technology is always the solution. It's more of a rich, you know, in a sense, pool of solutions, and you have to gauge, you know, based on experience and the requirements, what you should do. Another problem is that if you have smaller wavelengths, you also have, as it happens in millimeter wave frequencies, you also have smaller capture energy in an antenna, right? The larger is the wavelength, the more your antenna would capture energy, okay? It has to do with the size of the antenna, basically, right? So now I'm not an antenna engineer, but there are some issues with that. Of course, that's where possibly that's probably the single most important, you know, motivation to have millimeter wave combined with massive MIMO is that massive MIMO, because of what I said before, this 10 log 10 number of antennas gain in SNR can cope with this. So we have two issues here: increasing noise and decreasing signal power, but you have the array gain compensating that, right? And even in terms of the range of the cell, you don't have to think like okay, small cells are using maybe 3 gigahertz, and millimeter wave they use 60 gigahertz. Therefore, they're microscopic coverage. That's why you do beamforming. So it's more directional, yes, but roughly speaking, the range. So this is meant to be an alternative to small cells. It's not that you keep decreasing, shrinking forever. You still target kind of hotspot situation, but in a much more directional fashion. So, for example, if you want to have a hotspot kind of coverage, then a crowd service, right? Serving a crowd kind of transmission, and you know that the users are not moving, probably millimeter wave would make sense, okay? Because you don't have to track. But if you do have to track, then you have to be careful. Like, it might make more sense to use lower frequency, therefore not millimeter wave. So again, normally you have a set of requirements, you have a set of solutions, and the good engineer would do the matching, right? So it's not hard coded. It's more like this circuit switching system, right? You have to identify the best map. Yeah, another thing I want to mention close to the end. So the coverage, yes, it's a problem because the higher we go in frequency, we know it tends to attenuate faster with distance. Okay, but you do have the possibility maybe to use massive MIMO in an easier way, maybe than in lower frequencies. Another thing, there is a result from measurements from Rappaport group, Ted Rappaport in US, where they show basically that the loss with the frequency is not a monotonic function. So it does go up as a trend, but there are a lot of irregularities. So sometimes it happens that a lower frequency actually attenuates more than a higher one. It happens, and they're quite dramatic. So let's say the average yes of the loss goes up, but not the instantaneous value in terms of the frequency, right? So you do have a situation maybe like this. So if you play smartly, it could be that using a higher frequency, you attenuate even less your signal, okay? Another thing that people have been telling for a while, yeah, but when it rains, kaput, nothing will work anymore. Apparently not so true. Okay, so there are some myths also being basically, demystified, so to speak. So there are some things you can do. Of course, you can, configure your MIMO system, as we said. On the minus side, yeah, hardware might be a challenge. The fact that you have highly directional antennas and you always need to keep track of your users might be complicating the design quite a bit. Also control signals, how you do resource allocation, how you dimension your deployment. There are many things that will change, I think. Yeah, supporting mobility might be a challenge because of this user tracking thing I was saying, right? Now, when you talk about new spectrum, a lot has to do with policymakers. So this will become a big thing if we have the spectrum. If not, it will become just a set of papers, right? So now there are these world radio conferences happening every 4 years. next one is in 2019. So things are happening there where they assign the spectrum. So depending on how much spectrum we have and what spectrum we have in the millimeter wave band, this will impact definitely the work and the products. Yeah. Still, no matter what happens on the access side, this is already happening in terms of backhaul. So this is already being used as an alternative backhaul. For example, WiMAX does use this. Okay. On the access side, we have to wait a bit more and see what happens. So in summary, and then we stop for today, cooperative MIMO, it will be used because it's already there, basically. If you have better infrastructure in the sense of backhaul, good, it helps. But you need to be mindful of overheads, right? Because you have to exchange potentially a lot of information between base stations. In terms of the collocated massive MIMO, yes, it helps with system rates, needs a lot of antennas, can be used in collaboration with cooperative MIMO. What is most impressive about massive MIMO is the array gain. Array gain are really, really high, which means you can be very efficient also in uplink. You don't need to transmit so much, okay? So much power. The millimeter wave MIMO, this is what you should use if you really target peak rates over short range. It's meant for that because you have so much bandwidth that the throughput will just skyrocket in a sense. But it does require hardware work. A lot of work still needs to be done on the RF and circuitry and antenna side. It does require more spectrum, so somebody has to release the spectrum, and there has to be some policy decisions also. And in general, more radical system design might be there. Consider one thing, that the systems we have been using so far in the main, whether they are macro or small cells and so on, they never really were so dependent on directionality. Yeah, you might have it to help, but it wasn't a must. So this need to track the users in all directions wasn't really there. The first time I heard of this is with millimeter wave. So there are changes in the way you should design your control, your access, and dimension maybe your cells, that weren't there before the introduction of millimeter wave. So it's not a free ride. Okay, it might help in terms of some aspects, but it requires careful consideration. And in a sense, this is in order. Like if you go towards the bottom of the slide, this is increasingly more far-fetched. Okay, so these things are happening right now. This is at least prototype level and happening. This is something, it might not be in the early versions of 5G. So when they distinguish normally early 5G and let's say more mature 5G, normally millimeter wave is a discriminant. So you might have the first deployments without 5G for one reason, without millimeter wave. For one reason, mainly I think, is that they are also waiting to see what happens at the World Radio Conference of 2019. There the situation would be clearer, I think. Okay, and once you get a clearer picture on that, then there might be an accelerated deployment of the systems, and also many hardware challenges will be solved by them, right? So this is going to take a bit longer, and possibly the first deployments would have to wait the new decade, I think. Okay, so that does it for massive MIMO, and yeah, tomorrow we'll continue with application of massive MIMO to filter bank system. Yeah, thanks.